Hi. I've been hearing from a number of students in different sections that coming up sometime this coming up week is going to be quiz number 1. And it's a good idea to prepare for that. So I prepared some information just to try to get you thinking about what will be on quiz 1. How will I prepare? What will I do? What should I do? So let's have a look. Now, in this set of notes, I have a monstrous file out on my public website. I'm going to go show you a picture of it. This is a monstrous, I think it's 76 slides, and I don't want to drag you through all of this, but there's some bits and pieces of this monstrous file that might help you prepare for quiz number 1. So here's what I want to do. Let me show you how to get to this monstrous file so you can pick and choose slides that you might want to follow up on as a result of watching the video. Okay, so I'm going to go to my browser and then welcome you to Jay's Toolbox. So how do you get to Jay's Toolbox? Anybody can get to this site. This is a website, and it's at jaystoolbox.vt.domains. So this is open to anybody. This is beyond the Canvas site. Anybody can get to this site. Now, I'm going to show you how to get to this monstrous file I was talking about. Okay, we'll click drop down Toolbox and PowerPoint Documents, and then PowerPoint Topics. So this would be a PowerPoint topic you want to download. So I'm going to click on PowerPoint Topics, and I'm going to slowly scroll down. These PowerPoints are in no particular order, so I'm just going to slowly scroll down, and I found Test Success Tips. So there's two things. You can either click the download button or click Test Success Tips and download. So for example, so far 167 people have downloaded this PowerPoint file. So you can download it and then at your leisure, look through the material that's covered in this PowerPoint. Okay, I'm going to go back to PowerPoint, selected slides from there. Okay, and so now just a couple of slides on how to prepare yourself in general. And then I think the value of this video is going to be, I'm trying to think about potential things that might be on your quiz, right? So I have no knowledge of what's going to be on your quiz. All I can do is make some predictions. Okay, so how are you going to prepare when you step in there and you get your quiz? You want to quickly browse. It's probably going to be one problem or maybe a couple of problems, but browse, read those words, and think about how will you use your time, because it's going to be time limited. The next thing is, once you start working on your quiz, you want to monitor your time. Bring in either a stopwatch or bring in your phone that's got a clock on it to monitor yourself, monitor your own time. I've had students who have not bothered to do that, and then in the recap of the test, they said, yeah, I didn't realize the time was getting away from me. Monitor your time. Okay. Don't get mired down in doing calculations that are stealing a significant time away from you writing down with pencil and paper, outlining how to solve a problem. And certainly you always want to start with a sketch. That's worth a lot of partial credit. So rather than focusing on doing every calculation needed to get full credit, you're rolling the dice. Put down on pencil and paper how to communicate, how would you solve the problem. So it is common to be running out of time. That's a common dilemma. So allow time at the end of your allotted time to write down some fundamentals that apply to the solution. This gives you a chance to demonstrate how to solve the problem, not just a bunch of formulas, but fundamentals that apply to the problem at hand. It allows you to to write down that at least you understand how to move along in the problem without taking time to crunch numbers. So those are some tips I have for just sort of the basics of taking a quiz or taking a test. All right. Some key points about quiz 1. Start with a sketch. You've read the problem. Draw something down. Don't just start writing formulas down. Draw something down. A sketch of what's described. Is it an open system or a closed system problem? Write down one or the other of those phrases, open system or closed system. It communicates that you at least understood that basic. The chances on quiz 1 is that you're going to be using a pressure volume diagram or a pressure specific volume diagram if it's a closed system to solve the problem. So for example, if you can depict process 1 to 2 on a PV diagram, you can visualize the work out, and you probably will be asked about what is the work done for this situation. Show your work, explain your steps, and work down the page. Those are critical pieces of advice. Not the shotgun thing. Don't work from left to right and then down. Work down the page, step by step, working down the page. Are you lost? Are you, I didn't prepare well enough. Am I lost? A lot of times I tell lots of students, when you're totally lost, write down the first law of thermodynamics for a closed system. That's all you've got so far. First law for a closed system. A lot of times it's going to help spark your ideas. Oh, I see. I've written down the first law. Now I see where to go. That's another key thing if you're just totally lost. Write down the first law. Okay, you've prepared, you're ready. Be satisfied with the preparation you've made. There's only so many hours in a day. You're taking a lot of classes. Be satisfied with the way you prepared. Your evaluated performance, or in other words, your grade in the quiz, is usually a reflection of how you prepared. Now, a lot of that has to do with how you have done and solved the homework problems. Okay. So do be aware that your grade on the quiz is not a measure of what you know about thermodynamics. It's a matter of how you perform in thermodynamic problem solving. Okay, so those are generic things. In this monstrous PowerPoint file, I'm just jumping right to Appendix A, which is entitled Prepare for Quiz 1. So I felt like this could be a way to go through and give you some candidate questions that you might see on your quiz. So what I'd like to do is I'm going to ask the question that might be on your quiz. Think in your mind, what's the answer, or how would I attack the problem? And I'm going to spend little time on here's the way you solve the problem, because you can go possess this PowerPoint file and study on the detailed solution that I present here on your own. Give 4 examples each of an intensive property and an extensive property. Just give some examples. Intensive properties, extensive properties, Think in your mind, how would you do that? Here's a list of intensive properties that you should know off the top of your head. A list of extensive properties you should know off the top of your head. If not, certainly study on this. Go back to your textbook. Go back to your class notes. Chances are good. On short answers, you're going to be asked about intensive and extensive properties. What is the approximate boiling point of water at sea level? Include units. Do you know that off the top of your head? About, you don't have to be precise, about what's the boiling point of water at sea level, both in SI and English. Can you think of that? Could you write that down pretty quickly? Extra credit. Let's say you're on the top of Mount Everest. How would that boiling point be at the top of Mount Everest? How would the boiling point on Mount Everest compare to the boiling point at sea level? At this point, and I think in every section so far, you should be able to have a feel for that based on what you've covered in class so far. And there's the answers. But again, rather than spending time repeating the answers, you can go and look at those answers. Explain the difference between work and power. What's the difference? How are they similar? How are they different? Work and power. Work is the act of moving a force through a distance. And so this is the way I remember a generic way to express and to remember what work is all about. It's the integral of a force dx. And that also tells you the units are going to be a force through a distance or Newton meters. Okay. Power is different. Power is the rate at which this work is being done. And if you go to your textbook, you can fish out W dot. We put a dot over top of W to suggest or to depict power. W dot is d del W dt, the rate at which work is done. D by dt, the rate at which work is being done. So the units of power are watts, also known as joules per second. A watt is a joule per second, or kilowatts, or megawatts, or horsepower. That's the difference between power and work. Very important. That could definitely be covered in a quiz on short answer. Explain the difference between work and heat transfer. What is the fundamental difference between those two different forms of energy transfer? And what do they have in common? Okay, they have in common. Work, we just covered. Work is the act of moving a force through a distance, but heat transfer is energy transfer phenomenon that occurs only because of energy transfer between hot to cold. A temperature difference is what characterizes heat transfer. So work and heat are two dramatically different forms of energy. Both of those are called system boundary phenomena. They occur only at a system boundary, that dashed description of, let's say, a closed system. Work and heat occur across a system boundary, not within a system boundary. Oops. You should be able to do this in your sleep. I won't be surprised if you get, this would be a little bit like a short answer problem on a quiz. You should be able to do this back and forth in your sleep. All you have to remember is that to go from degrees C to degrees K, simply add 273. Degrees C to absolute temperature. Degrees Fahrenheit to absolute temperature. Degrees R, degrees Rankine, add 460. Add 460. And then it's my hope that you've memorized the degrees F to degrees C conversion, hopefully that you learned in high school. What's the difference between absolute pressure and gauge pressure? I would not get nervous about this. The only related quiz problem that you might have might be determine the pressure at the bottom of a tank. Sounds like a homework problem, doesn't it? For nearly all sections, okay? And you might be asked the difference between a pressure gauge at the bottom of the tank versus the absolute pressure at the bottom of the tank. So I wouldn't spend a great deal of time, as you're preparing, I wouldn't spend a great deal of time doing this. Okay, and these are notes about the difference between gauge pressure, absolute pressure. I've created a video about this. You could click on the video and spend a little time refreshing your memory on the difference between gauge pressure and absolute pressure. Here is a word problem that you may well see. This was a quiz problem that I gave when I was an instructor in thermodynamics. An elevator is designed to lift a mass of 1,000 kilograms of people and the elevator car. The cables must lift the elevator car a distance of 12 meters in 20 seconds of time. Question is, one question, what is the minimum average electric motor power in kilowatts required to accomplish this? And here's a picture of people being raised in an elevator a distance of 12 meters. This is a reasonable quiz question. Okay, what would be the approach? What would your solution look like if this was your quiz question? Well, here's a sketch. I'm showing 1,000 kilograms, closed system. It's just a fixed mass. I've shown must lift 12 meters in 20 seconds, and I've shown an arrow and a distance. That's a decent sketch, okay? I need the weight. I need to transform the mass into a weight, okay? You're probably pretty good at that. We don't need to show you how to do that. What work is done? It's a force through a distance. And so, gosh, in the quiz situation, you don't need to write through all the fundamentals. You can say the work needed is the work, which is the W times the height, the force through a distance. That probably would work, okay? And then the average rate of work is the work that you just found divided by the time, work divided by time. That's going to get you a good bit of partial credit just writing those things down. And then here's the numerics. Here's the numerics of the problem. That could go pretty fast if you have a good handle on the fundamentals. So again, I'm not going to drag you through this and spend time doing every single step. You can go get this PowerPoint slide and study it to get more comfortable with how would you solve it completely with the numerics. What are the engineering requirements for this relationship that I hope you've been using a lot? W out, the work done by a system, is the integral of PdV. What engineering requirements are for that? That's not always true. So that statement is not always true. You need to know. Okay. Two basic closed system. This is true for a closed system, and you've got to have pressure as a function of V. In other words, pressure has got to be described in a formula or an equation. Okay. So for example, when you can describe P as a function of V, that would be considered similar to stating quasi-equilibrium process. So a quasi-equilibrium process in which the pressure path as a function of volume is known or defined. Okay, closed system, quasi-equilibrium process, or in other words, P has got to be a function of V so you can do the integral. Now I'm jumping to Appendix F, and this is a little bit of a value add that I added a couple of weeks ago for you folks particularly, okay? I think it's 4 example quiz questions that the probability is even higher that you might see something like this. What's the purpose of reading the problem? Purpose of reading a problem before you start working on the numbers is what information is provided and what do you need to determine. That's critical in a time-limited situation. In most cases, you won't be given a sketch of the situation. Mostly it's going to be a word problem. So is it a closed system or open system? Start with a sketch. Can a PV diagram help me, or some other diagram? What are the key words that help you solve the problem? So these 4 examples are illustrations of word keys within the problem that will help you solve the problem. Okay, example 1, I'll read it to you. This is classic wording of a quiz. Let me move my picture down. A gas is contained within a vertical cylinder fitted with a 5-centimeter diameter piston. The height of the piston above the bottom of the cylinder is 25 centimeters. The downward forces acting on the piston are held constant at 50 newtons. Heat is added to the gas until the volume doubles. How much work is done by the gas on the piston? That is as basic a thermo quiz question as you can get. How would you affect? We just read it. Where would you go from here if this was a quiz? Draw a sketch. Okay, there's the problem statement repeated. Key words, piston and cylinder. That means it's a closed system. Okay. There's enough information in there to determine the initial volume. Okay. Volume doubles. So V2 equals 2V1. That's getting you something. Okay. The downward force on the piston is given as constant. That means, if you think about it, the process is a constant pressure process. If you think about the force balance, the free body diagram on the piston. Okay. Here's some things I would expect. If I'm grading your quiz, here's things I would expect you to see on your quiz solution. Here's the volume. Here's an expression for the volume, final volume, 2V1. Here's an expression for the area, pi over 4d squared, okay? Here's an expression for the pressure, showing that the pressure is constant. P1 equals P2 equals 50 newtons divided by A1. That's buying you a significant amount of partial credit. Here's the sketch of the piston and cylinder showing the closed system. H1 and H2 was given, okay? Or you can find H2, okay? A visualization of the work done. A PV diagram is worth a lot on this problem. Pressure, volume, constant pressure process, V1, 2V1, double the volume. And then finally, pull P out of the integral because it's constant pressure. How would you evaluate the work? Integral of P dV, pull the P out, P integral dV, that's an easy integral. It's just V, evaluated from 1 to 2, P times V2 minus V1. So without going through the numerics, boom, that's going to buy you a huge amount of partial credit on your solution. Example 2. A 2 kilogram mass of gas is contained inside a rigid vessel with a volume of 5 cubic meters. Vessel has 5 cubic meters. Initial pressure is 100 kPa. Initial temperature is 25 degrees C. Heat is added to the gas until the temperature reaches 150 degrees C. Gets hotter, okay? How much work is done by the gas during the process? What's the initial specific volume? What's the final specific volume? What's the initial density? What's the final density? Wow, that's a lot of questions. It turns out that this is an incredibly easy problem, isn't it? I hope you've seen through it. Wow, lots of information given, but this is really easy. Sketch, closed system. Okay, closed system. M, I wrote that M is given, V is given. Wow, you got to know what's the definition of specific volume? Capital V over M. Oh, we can do that in 5 over 2. 2.5 is the initial specific volume. Density. Density is mass over volume, or 1 over the specific volume. Density. It's 2/5, 0.4. PV diagram. A rigid container, the volume is constant. Wow. So that means that the initial specific volume exactly equals the final specific volume, and the initial density exactly equals the final density. Work out as the integral PdV. I can see this with my eyes. What's the area under the curve, 1 to 2? Integral of PdV. It's 0. Answers. How much work done? 0. What's the initial specific volume? 2.5 cubic meters per kilogram. What's the final specific volume? 2.5 cubic meters per kilogram. What's the initial density? 0.4 cubic meters per kilogram. What's the final density? 0.4 kilograms per cubic meter. Boom. This kind of thing. My first thermo professor was famous for doing stuff like this. Example 3, a gas is contained within the cylinder fitted with a piston. Piston and cylinder, closed system. The mass of the gas within the cylinder is 3 kilograms. It has an initial pressure of 500 kPa and an initial volume of 1.5 cubic meters. Now it says a slow quasi-equilibrium force, it's variable, is applied to the piston such that the gas undergoes a process where P times V is constant until the volume triples. The only question is how much work is done by the gas on the piston. That's the only question. How much work is done? How would you approach this problem? Are you seeing how you do this? Well, we'll start with a sketch. Piston and cylinders, closed system. That's worth a little bit, okay? P times V is constant. I hope you immediately see that the shape of the process is a hyperbola. Okay, should immediately see this. PV is constant. In your section, you've probably had enough homework problems to see that, to know this. Okay, constant. And so I would P1 and V1 are both given. I'd calculate the constant first. However, you're looking for the work. Work is integral PdV. Okay, I need pressure. In terms of volume. Well, P is constant over V. P is constant over V. Constant, I'll pull out of the integral. I'll do the integral. 1 over V dV. That's the natural log of V, evaluated from 1 to 2. Natural log of V2 over V1. Now, V2 minus log of V1. Okay, work out as constant times. Well, it's just algebra. The log of V2 minus the log of V1 is the natural log of V2 over V1. And I believe, look at this, V2 is 3V1, so it's the natural log of 3. This is classic quiz situation where you don't even have to do a lot of calculations. You have to calculate the constant P1 V1 times the natural log of 3 to get the work out. Not bad. Classic. This is a classic quiz question. Here's another more difficult classic quiz question. Very similar to example 3. A gas is contained within a cylinder fitted with a 5 centimeter diameter piston. The mass of the gas within the cylinder is 3 kilograms, has an initial pressure of 500 kPa, and initial volume of 1.5 cubic meters. P1, V1 given. A slow quasi-equilibrium force is applied on the piston. So the gas undergoes a process where P times V to the 1.4 power is constant, and the volume triples. Sounds a lot like example 3. How much work is done by the gas on the piston? Very similar to example 3, okay? It does look like I've got some crazy exponents all goofed up around here, but here's my sketch. Closed system, piston and cylinder. Now, PV of the 1.4 is not a hyperbola. It's a little steeper than a hyperbola. Looks the same, looks similar, a little steeper, okay? Same approach. Work out, that's what I'm looking for, is integral PdV. I need pressure as a function of volume. So here it is. Here's what's given. P is equal to constant times V to the minus 1.4. I've got to do the integral. Tougher integral. Tougher to evaluate. I encourage you to get this slide deck and study this. Don't have to memorize it because you've got to be able to do the integral on your own. And then you would evaluate the numeric. So this integral is not trivial. I see this given by professors, instructors all the time on quizzes now, okay? So this integral is not trivial. You've got to understand how to perform it. Writing down a formula on a formula sheet will not win the day on this. You've got to be able to do this integral on your own. So that's what I've got. So we've gone through a good number, maybe almost about 10 examples of candidate things that you might see on your quiz. So this is a little better than going in blind, going in not knowing what to expect. It is my hope that you see some things like this, and I hope that this video helped you prepare for your upcoming quiz. Okay, so that is it. I wish you the best of luck on your quiz. Good luck. Let me know what I can do to help.